Assalamu alaikum dear students. This is 22nd lecture of probability and stochastic processes. We have been working with a scalar valued random variable which assumed its value based on the values assumed by two other random variables. So this random variable was indirectly defined through the two other random variables. And this transformation was a function with domain being a two-dimensional plane and range being the real line. So we took two values assumed by two random variables and transformed these values to make a singular value, a scalar value, which was the value of the new random variable that we defined. We were working with an example of two television sets. The two television sets were made by two different manufacturers, and we modeled their service time or time before their failure. And we modeled the service time of our first television with random variable x and service time of the second television with random variable y. We assumed that these two televisions fail independent of each other, and both of them follow exponential distribution with parameters of 0.1 and 0.05. The parameter value of lambda of 0.1 was for television X, and value of lambda for television Y was 0.05. And it was assumed that television X was less reliable and television Y was more reliable. We found the joint probability density function of random variables x and y, which was defined over the first quadrant of xy plane, and from this joint density we found the PDF and CDF of random variable z. We worked with two examples of transformed random variable z. The first was when we modeled the random behavior of total service time of two televisions. The two televisions fail independent of each other, giving some service time. But we were interested in finding the random behavior of the sum of two service times. So our random variable z was x plus y, where x was the service time of first television and y was the service time of second television. We found the CDF and PDF of random variable z from the joint PDF of random variable x and y. And once we know the PDF of random variable z, we were able to answer questions about the behavior of this random variable z by directly processing the PDF of z. The kind of questions that we were able to answer were: what is the probability that total service time will be between 24 and 36 months, between 2 and 3 years? Or what's the probability that the total service time of the two televisions is more than 60 months or 5 years? So these type of questions were answered by processing the PDF of z directly without referring to the joint PDF of x and y. The other example of a third random variable being defined on two other random variables was when we looked at the random behavior of the difference of two service times. We wanted to find if the two televisions fail at different times, what is the behavior of the difference between two failure times or difference between the two service times. And the random variable that we defined was z is equal to y minus x. So we took the service time of y, the more reliable television, and subtracted from it the service time of x, the less reliable television. And then we were able to find probability of different events defined for this random variable z, which was the difference of two service times. And we were able to answer questions like: what is the probability that the difference is less than a certain value or the difference is more than a certain value. These questions made sense because we found the probability of y minus x being greater than 20, or in other words, probability of more reliable television Y failing at least 20 months later than the less reliable television, and probability of this event came out to be 24.5%. And in the reverse, we also found the probability of y minus x being less than minus 20, or x minus y being greater than 20, or the less reliable television failing at least 20 months after the more reliable television fails. And this probability came out to be a small number of 4.5% as expected. Analysis of a random variable z, which is difference of two random variables y and x, is an interesting way to measure the relative performance of two televisions. When we define this random variable z to be y minus x, we can answer questions like, what is the probability that one television fails before the other television and other television fail at least a few months later than the first television. There is another way to measure the relative performance of two televisions, and that is when we take the ratio of their service times. So instead of defining our z to be y minus x, we will be defining the new random variable z to be y over x. These two ways to define two random variables to measure their relative performance has their own merits and demerits. When you take the difference of two random variables, you are taking the absolute value of the two service times, the difference of two service times. So if you are interested in finding the probability of one television failing at least 20 months later than the other television, then they can fail in such a way that first television fails after 2 months and the other fails after 22 months. Or the first television can fail after giving you a service time of 20 months and the other television fails after 40 months. These two scenarios have different meanings. In the first case, the relative performance of the first television was much worse than in the second scenario. To count for that, we take the ratio of the two service times. If we take ratio and we are interested in the ratio being smaller than a certain number or larger than a certain number, then the relative amount of the service times follows this ratio. So we are going to define the next random variable that we are analyzing to be z is equal to y over x. When you define your new random variable z to be y over x, then z is only going to assume positive values because it is the division of two service times and both are positive numbers. For this random variable, if we find the probability of z being less than a certain number, for example 1, then it implies that y over x was less than 1 or x was larger than 1, or the less reliable television x was able to beat the more reliable television y in terms of the service time. So if y over x, which is z, is less than 1, then x beats y, and if y over x, the new random variable z, is greater than 1, then y, the more reliable TV, beats the less reliable. You don't have to take 1, you can take a value of 0.5 or 2 so that the relative performance of the two television is with a factor of 2. If y over x is less than 0.5, then x beats y with a factor of 2. And if y over x is more than 2, then y beats x with a factor of 2. Let's look at this slide, which shows that for different values of z, which is y over x, what are the regions of the first quadrant which get integrated to find the probabilities of different values of z. On your slide, you can see that the sand hill representing the joint probability density of x and y has been divided in such a way that the regions represent this ratio to be less than 0.25, 0.5, 1, 2, and 4. We can use these regions to find the probabilities of different events defined on z. Actually, we are going to find the CDF of z by finding the probabilities of such regions. If you look at your slide, you will see that if we want to find the CDF of new random variable z, that is capital F z of z, then we have to integrate the joint PDF over a triangular shape region which is bounded from below by x-axis and from above by a straight line with equation y is equal to zx. The total volume of the sandhill in this region corresponds to the probability of event that z is less than a certain value of parameter z, the small z. So by changing the value of this parameter small z, you can find probabilities of different events, and these probabilities as a function of small z give us the CDF or cumulative density function of new random variable z. So as you increase z, the region of integration starts making bigger and bigger triangles until it reaches infinity, which is slope of 90 degrees. So by using this procedure, you can easily integrate different triangular regions to find CDF, and that CDF comes out to be as a function of z, the small z, as z over 2 plus z. The CDF is only defined for positive values of z because the random variable z, which is the ratio of two surface times, only assumes positive values. So this formula of CDF, which is z over 2 plus z, is only defined for positive values of z. So the CDF is 0 for negative values of z, it is 0 for z is equal to 0, and for positive values of z, it rises and eventually reaches a value of 1 for very large values of z. This CDF is plotted, and you can see this on your screen, and you can see that this CDF rises very sharply in the beginning, and then it tapers off and slowly reaches its final destination. This sharp increase in the beginning, which has a large slope, should give you some hint about the shape of the PDF, which is the differentiation of CDF. So if you look at this CDF and imagine taking the slope of this curve, you will get the shape of the PDF. And you can analytically find the expression for the PDF by taking differentiation with respect to z of the expression of CDF, which is z over 2 plus z, and the expression as shown on your screen comes out to be 1 over 2 plus z minus z over 2 plus z whole square. And if you plot this PDF, you will see that the PDF takes a large value initially, and then it takes on smaller and smaller values for larger values of z. Apparently, it looks like the PDF of an exponential distribution, but it is not. The shape is similar, but if you look at the expression, you can clearly see that this PDF is not an exponential distribution. Now that we have found the PDF of this new random variable z, which is defined to be y over x, we can answer few interesting questions about the behavior of this new random variable. Let's find the probability of x beating y by a factor of 2. That is, x is larger than 2y. But we have defined our random variable to be y over x. We will rearrange the term, and x greater than 2y comes out to be y over x being less than 0.5. We have the PDF of this random variable z, and we can find the probability of z, which is y over x, being less than 0.5 by taking the integration of this PDF from 0 to 0.5. And if you find this integral, its value is 0.2. So probability of less reliable television x beating the more reliable television y in terms of the service times by a ratio of 2 is only 20%. You can find the probability of the other case where y beats x by a factor of 2. In that case, y is going to be greater than 2 times x, or y over x being greater than 2. To find the probability of this event, all you have to do is find the integral of this PDF of z from 2 to infinity. And when you find this integral, it comes out to be 0.5. So probability of more reliable television y beating less reliable television x in terms of the service times by a factor of 2 is 50%, and the probability of the reverse case is only 20% as expected. The next random variable that we are going to work with is z is equal to x into y. So there are two random variables x and y. They take on their respective values, and we multiply the values to get the value of our new random variable z. If we are looking at the behavior of two televisions or the service time of two televisions, if we multiply the two service times, the quantity that we get has no real life meanings. You get a service time of 10 months from first television and 20 months from second television. You multiply them together, get a value of 200 with units of month squared, and it makes no sense. But this random variable z is equal to x into y can have other real life implications for other problems. For example, if you pick a random point in the first quadrant of xy plane, then the point will be x comma y. The values of the points, the x coordinate will be x, y coordinate will be y. Suppose these two values are random, so the location of your point will be random, and you can assume the two values x and y to be independent or dependent on each other. In any case, if you pick a random point in the first quadrant of xy plane, then you will get a rectangle with lower left point at origin and upper right point at x comma y. And the rectangle will have an area of x into y. X will be the width of the base, y will be the height of this rectangle. And if you have your x and y as random variable, then the area of this rectangle with lower left point at origin and upper right point at a random point x comma y will be x into y. So this new random variable x into y can have practical implications for some cases, but for the case of two televisions, it has no real life meaning. But to continue with the joint density that we defined for the two televisions, we are going to find the probability density function, or CDF, for this random variable z is equal to x into y for the same joint density of two televisions, even though this random variable has no real life meaning for the case of two service times of two televisions. So if you look at your screen, you will see the way the sand hill is going to be divided for evaluation of the CDF of the random variable z equal to x into y. Since this random variable z, which is equal to x into y, only takes positive values, we are going to find the CDF of this random variable z by finding the probabilities of this random variable z being smaller than the value of parameter small z. And if you look at this slide, you can see that the sand hill is divided in such a way that the region closest to origin represent the probability of z being less than 5. And the next dividing line represents the probability of this random variable z being less than 20. The next dividing line represents the probability of this z being less than 50, and last dividing line represents the probability of random variable z being less than 100. So as you keep on increasing the value of parameter from 5 to 20 to 50 to 100 and beyond, you include more and more region of the sand hill for integration to find the probability of these parameters, which are going to give you the CDF. On the next slide, you can see how this integral is going to be evaluated. The region which is going to be integrated to find the CDF is bounded from below by x-axis, from left by y-axis, and from above by a curve y is equal to z over x. So you pick a value of z, and then this curve y is equal to z over x is going to be the boundary of the region which is going to be integrated to find the CDF for that particular value of z. This integration is found as a double integral where initially the volume of the sandhill along a narrow vertical strip is found, and then these strips are taken over the whole extent of the x-axis. And you can see on your screen this double integral, which is initially evaluated along y and then along x. The integration along y just takes the joint PDF of x and y, and the extent of this integration is from 0 to z over x. And once you have evaluated this integral, then you take integration along x from 0 to infinity. If you try to find closed form solution of this double integral for this particular case of joint PDF, which is the multiplication of two individual exponential distributions modeling the behavior of two televisions, you will find that closed form solution does not exist. But if you had some other simpler joint density, like a flat density defined over a certain region of xy plane, you could certainly hope to find a closed form solution. So if you cannot find a closed form solution, you can certainly go to numerical techniques to find the CDF, the PDF, and probabilities of different events. I'm not going to do that, so I'm going to start the discussion on the next random variable that we are going to analyze. The next random variable that we are going to talk about does not measure the relative performance of two televisions, but it measures our total length of enjoyment that we get from the two televisions. So suppose you buy two televisions and one of them fails early, within 3 or 6 months, it could be X or Y, but the other fails much later. So as long as one of the two televisions is working, we are somewhat happy and we can enjoy the television broadcast on at least the television which still works. So the random variable that we are interested in is max of X and Y. So if X is the failure time of television X, Y is the failure time of the other television, then we take the maximum of the two failure times to get the maximum time duration during which we can watch television at least one of them. In previous lecture, a similar example was quoted where I told you that if we had an airplane which had two engines and airplane could safely fly on at least one of the engines, then as long as one of the two engines is working, we are safe. So imagine you are flying in that airplane and the pilot announces that one of the engine has failed. So you will be slightly unhappy, but still you will be alive and you will be hoping that you will survive this journey and land safely. Once the pilot makes that announcement, of course, your level of happiness will be lowered and you will not be doing frivolous things, but you will be looking up towards heavens for help from forces unseen so that the other engine does not fail during the remaining time of the flight. But as long as one of the two engines is working, you are safe and hope to land in a single piece. In case of televisions, you are happy as long as one of the two televisions is working. So the random variable that we are interested in is Z is equal to max of X and Y. So if X fails at 2 months and Y fails at 30 months, so value of the random variable Z is 30. Similarly, if X fails at 25 months but Y fails at 7, the value of Z, which is max of X and Y, is the value of X because X fails later. For this random variable Z, we can find the CDF and then from CDF the PDF, again by following the same procedure where we look at the first quadrant where the joint density is defined and we find probabilities of events like capital Z being less than or equal to a number small z, which is a parameter. We vary this small z, the parameter, and find probabilities of the events capital Z being less than or equal to this small z. As this small z changes, the value of the probability changes, and that value of probability as a function of small z is the CDF. And from this CDF, you can certainly find the PDF. So let's look at region of the joint density, the regions of first quadrant where joint density of X and Y is defined, to see how this region is divided as we take larger and larger values of Z. You can see on your screen that as we keep increasing the value of parameter small z, we get larger and larger regions of the first quadrant that contribute towards the integral, which gives us value of CDF for particular value of small z. And the shape of this region is square. So if you take a value of z to be 5, then this square is a 5 by 5 square with maximum value of either x or y is going to be 5. Similarly, if you take value of small z to be 10, then all the points x comma y where both of them are smaller than 10 are going to be included. So as you keep on increasing the value of small z, this square keeps on moving to the right with the corner being at z, z. On your screen, you can see the regions that correspond to capital Z being less than 5, 10, 20, and 30 months. And you can take other values of small z and find the CDF. It's easy to see that if the region to be integrated is a square, then the CDF of this new random variable z is very easy to find, because the probability of this square type regions is very easy to find through the CDF of x and y. On your screen, you can see that the formula for CDF of capital Z, the random variable, for a certain value of small z comes out to be simply multiplication of CDF of x and y, where the parameter values instead of being x and y are simply small z. So if you multiply the two CDFs of x and y by replacing both x and y with z, you get the expression which represents the CDF of new random variable z. And on your screen, you can see that this expression comes out to be 1 minus e raised to power minus z over 10 minus e raised to power minus z over 20 plus e raised to power minus 3z over 20. From this expression of the CDF, you can guess the shape of the CDF. The expression is 1 minus 3 terms which are functions of z. These 3 terms, 2 with minus sign and 1 with positive sign, are all 1 for values of z being 0, and they are all 0 for very large values of z. So for z is equal to 0, there are 2 terms which are positive with a value of 1 and 2 terms which are negative, so it will be 0. And for large values of z, all 3 terms will be 0, and our CDF will approach its destination of 1. But you cannot say that this is the CDF of an exponential distribution, because in exponential distribution there is only one factor after 1. So if it was 1 minus e raised to power minus z over something, then it would be a CDF of exponential distribution. Now you cannot say that. To actually see the shape of this CDF, you can plot this expression, and I have done that for you, and you can see this plot of CDF on your screen now, and you can see that CDF starts at 0 with very low slope. It's almost parallel to the x-axis. Then it rises and then it tapers off and becomes 1. From this shape, you can guess the value of the PDF, or actually the shape of the PDF, which is the differentiation of this CDF. If you differentiate this CDF, which starts with 0 slope, then rises and eventually becomes tapering to final destination value of 1, you can see that initially PDF is going to be 0 because the slope is initially 0, and finally PDF again is going to be 0, and in between the PDF is going to have non-zero value. You can easily differentiate this expression and plot the PDF, and you can see the plot of the PDF on your next screen, where the PDF has an expression of 0.1 e raised to power minus z over 10 plus 0.05 e raised to power minus z over 20 minus 0.15 e raised to power minus 3z over 20. And the plot of the PDF is not the plot of the exponential distribution. It starts at 0, goes to a high value, and then it goes down. Now that we have found the CDF and PDF of this random variable z, which is max of x and y, we can answer some interesting questions about the behavior of this new random variable z. The first question that we are going to answer is that what is the probability that this random variable z is less than 3 months? That is, the maximum of the service time is smaller than 3 months, or in other words, both televisions fail during the first 3 months. If you want to find the probability of this event, all you have to do is integrate the PDF of z from 0 to 3. And when you do that, it comes out to be 0.036. So there is only 3.6% chance that both televisions will fail during the first 3 months. The next question that we want to answer is that what is the probability that this new random variable z takes on a value which is larger than 30 months? Or in other words, what's the probability that after 30 months of our initial purchase of 2 televisions, we still have one of the televisions working? We can have both of them working, and that is very nice, but even if one of them fails, we are still happy, slightly less happy, but still happy. So probability of that event can be found by integrating this PDF of z from 30 to infinity. And when you do that, the probability comes out to be 0.262 or 26.2%. By the way, we are not considering the event where both of the televisions are working in this region of 30 months to infinity. If you demand that both of the televisions are working in this interval, then probability of that event comes out to be only 1.11%. We are allowing one of the televisions to fail and other to continue giving us service beyond the 30-month deadline. So if you demand that both of your televisions must be working after 30 months of their purchase, the probability of that happening is a small number of 1.11%. But if you lower your expectations and allow one of the televisions to fail and still be happy, then you will be happy with slightly less level of happiness, but probability of that happening is 26.2%. So moral of the story is, if you lower your expectations, then probability of you being happy with lowered expectations is going to be larger. The next variable that we are going to work with is z equal to min of x and y. For the case of 2 televisions, this random variable z, which is equal to min of x comma y, represents the random duration during which both of the televisions are working. So if one television fails at 3 months, the other fails at 12 months, we are going to take 3 as the value of z. So it represents the duration during which we are extremely happy and we can watch whichever television we want to. And for the case of airplane with 2 engines, this random variable z, which is equal to min of x comma y, where x and y model the failure time of 2 engines, represents that duration of time, the initial duration of our journey, during which both engines are working properly and we are not looking up towards heaven for help. In any case, this random variable z, which is min of x and y, can be analyzed by finding its CDF and then its PDF. To find the CDF, we will take integration of those regions of the joint density of x and y where the min of x and y is below the value of parameter small z. On your screen, you can see that the joint density of x and y has been partitioned in such a way that for first region, the minimum of x and y is smaller than 5. So total volume of this part of the sandhill represents the probability that z, which is min of x and y, will be smaller than 5. The next partition represents the probability of z being less than 10. The third partition represents the event where z is less than 15. And fourth partition of the joint PDF represents the probability of event where capital Z is less than 20. Of course, if you want to find the CDF of random variable z, you will continuously vary this parameter small z and find the CDF of z in terms of the joint PDF of x and y. Once again, because this region of joint PDF is such a region where the remaining portion is a square, you can easily find the CDF of z by properly relating this region to the CDF of x and y. And if you look at your screen, you can see that the expression for CDF of z for this particular case comes out to be 1 minus the multiplication of 1 minus CDF of x and 1 minus CDF of y, where the parameters x and y has been replaced by the parameter small z. If you open these expressions and simplify the terms, the CDF comes out to be 1 minus e raised to power minus 3z over 20. And you should be able to guess that this CDF is CDF of a purely exponential distribution with value of alpha being 3 over 20. Since you have worked so extensively with exponential distributions, their CDFs and PDFs, I'm not going to analyze this particular random variable any further. This random variable min of x comma y for this particular case of joint PDF, which is multiplication of two exponential distributions, again gives us an exponential distribution, and you can find probabilities of interesting events for this random variable z, which are nothing more than simple processing of exponential PDFs. The next random variable that we are going to analyze is defined from two random variables x and y as z is equal to square root of x square plus y square. So if two random variables x and y take on their respective values, which are random in xy plane, then the random variable z is the direct distance, the Euclidean distance from origin to the point representing the two coordinates x and y, where x and y are values of random variable x and y respectively. There are many situations in real life where such a derived random variable is of particular interest. For example, if there is an archer who is trying to hit a target with his arrow and a bow, he is not going to hit the target exactly due to turbulence in the air and due to unsteady nature of human muscles. So he is going to aim at the center of the target, but the point which he is actually going to hit will be somewhere around that center. If we assume that the center of the target is at the origin, then the point that the archer is going to hit will have an x component and a y component, and you can model or assume that these x and y values, which are random, are going to follow certain distributions. And if you assume that, you can find the probability of the distance from origin of the point that is actually hit. And then you can answer interesting questions like, what is the probability that this distance is less than a certain value, which is the radius of the central circle. The target for archery is usually concentric circles, and you get more points if you hit the arrow in the central circle and less points if you hit the arrow in the ring around the central circle, and even less points if you hit the outer ring. So you can model this behavior and find the probability of this random variable z, which is the distance from origin to the point hit, and then you can find probabilities of this z being in this region, which is from 0 to R1, or z being from R1 to R2, the second region, or z being from R2 to R3, and you can even find the probability of z being away from the center by a certain distance, which is the size of the board, which represents that arrow is going to hit a wall or somebody standing next to the target. Another application of this type of random variable is in military applications, where you know the location of a target and you are trying to hit it with unguided rocket or a grenade, rocket launched grenade. So you make your calculations, you aim and then you fire, but due to turbulence in the air and many other factors, your grenade or rocket is not going to hit the target exactly. It's going to hit somewhere around that desired target, and you can model the x deviation and y deviation using some probability density function, and then you can find the probability of your grenade or rocket hitting the target or hitting a point which is within a certain distance from the center of the desired target. In any case, for this random variable z, which is square root of x square plus y square, you can find the CDF and PDF by following the same procedure we have been following, by looking at the whole xy plane where values of x and y are going to be assumed, and then taking larger and larger values of small z and finding the probabilities of capital Z, the distance, being less than this variable small z. On your screen, you can see that I have taken a joint Gaussian density representing the two variables x and y, with further assuming that x and y are independent of each other, and then I have taken a few regions which represent probability of z, the distance from origin, being less than a certain value. The first region in the center, which occupies the peak of this hill, represents all those points such that capital Z, the distance from center to the point xy, is less than or equal to 5. The larger region represents the probability of capital Z being less than or equal to 10. The next circle represents the probability of Z being in range of 0 to 15, and the last circle represents this capital Z, which is distance from origin to a point x comma y, being in the range from 0 to 25. You want to find the CDF of this random variable Z, you can continuously increase this parameter small z and find the probability of bigger and bigger regions of this sand hill, and you get your CDF. It's not very difficult to find the CDF of random variable z being defined as x square plus y square whole square root, particularly when the joint probability of x and y over which it is defined is product of two independent Gaussian random variables. Unfortunately, this evaluation requires long expressions which are not suitable for viewing on a television screen. So I leave it as an exercise for you to take two Gaussian independent random variables, form their joint density, and then find the CDF and PDF of a random variable z, which is defined as square root of x square plus y square. Today we worked with a few other examples of a random variable z being defined by using two values attained by two random variables x and y. We found the CDF and PDF of this newly defined random variable from the joint PDF of x and y. And then we were able to answer interesting questions regarding the behavior of this new random variable z. In next lecture, we'll continue to work with the behavior of random variables defined over pair of scalar valued random variables. Till then, I wish you the best. Thank you. Khuda Hafiz.